Okay, in this video, we're going to look at the derivatives of exponent and log functions. In our book, it does not come up until chapter 5. However, I want to introduce it earlier so we can do more practice with it throughout the year. Just a review on logs, if you have b to the x equals y, you can rewrite that as log base b of y equals x. Okay, take a minute and read over that if you forgot about that. Recall, the ln of x is really just log base e of x. Log of x is really log base 10 of x. And x is referred to as the argument. Now, before we actually start finding the derivatives of logs, I want to make sure that we review how to find the domain of a log. So for example 4, and these examples are going to be out of order. If I have g of x equals log of x squared minus 3x plus 2, find your domain. For log functions, my domain, I cannot take the log of a negative number. So I'm going to do x squared minus 3x plus 2 has to be just greater than 0. Now this actually factors into something pretty nicely. Factors into x minus 2, x minus 1 is greater than 0. Now you cannot just set each of those factors greater than 0 and solve. Remember, these give us, so when x is 2 and when x is 1, that gives us those critical values that we have to test the region between 1 and 2. So when we do that, when we pick values, less than 1 works, between 1 and 2 does not work, and greater than 2 will work. We'll make that original inequality of x squared minus 3x plus 2 truly greater than 0. So my domain of this, and this is one way you could write it, is for all x's, x has to be less than 1 and greater than 2. Okay. Some other properties of logs, if you have log base b of mn, you can really split that up into log base b of m plus log base b of n. If you have division, that's really subtraction. And if you have an exponent, you can drop that exponent down in front of your log. If you have log base b of b to the x, that's the same thing as x, or the same thing as b to the log base b of x. All right, and then the last one is your one-to-one property, so that also can be used. All right, so your derivatives. We're going to start with ln's because they're a little bit easier. The derivative of ln of just x is 1 over x. The derivative of the ln of the absolute value of x is also 1 over x. But the derivative of ln of u, where u can be anything but x, so this is anything but x. Then my derivative is 1 over u times the derivative of u. So that's actually using a chain rule. So, example 8, find your derivative of each of the following. Well, first, for h prime, I have to do a chain rule because I have a cosine. So the derivative of the outside is negative sine times the inside times the derivative of the inside. The derivative of ln of x is 1 over x. So I would probably rewrite it and say my derivative is negative sine ln of x over x. So that one was pretty straightforward. In part B, I have y equals the ln of 1 plus the ln of x. So I'm going to do y prime. The ln of some u is going to be 1 over that u thing, right, times the derivative of that u. Okay, and by u I mean u is 1 plus the ln of x. So the derivative of 1 is 0, the derivative of ln of x is 1 over x. So that means then that y prime is 1 over x times 1 plus the ln of x, which is the same thing as x plus ln, 1 over x plus x ln of x, which is actually the same thing as 1 over x plus ln of x to the x. The only reason I want to rewrite it a couple different ways is just to remind us of some of our log rules. All right, for C, first I would probably rewrite this before I try to find the derivative. So I'm just going to rewrite it so that f of u is really just the ln of 3u plus 2 over 3u minus 2, the whole thing to the 1/2. Then what I'm going to do is actually rewrite it by using my power rule and put that. So I'm not doing derivative yet. I'm simply using all of my ln rules. Then I can break that apart even more and simply say that fu is 1/2 times the ln of 3u plus 2 minus, I'm gonna factor out the 1/2, so I'm gonna write 1/2 times and then 3u minus 2. Now what I would like you to do at this point, try to differentiate this and then check my work. So in red is me taking the derivative of that fu function after I simplified it using my log rules. So take a minute and check over that. Now, we can also do derivatives of log when they have a base. So when it's log base b of x, that becomes 1 over x times the ln of b, so the ln of my base, which simplifies to 1 over x ln of b. That will be the same thing if my argument's in the absolute value. Now, if I have some u, so if this is not just an x, and I get 1 over u times the ln of b times the derivative of u. Okay, so that again is using my chain rule. So let's take a look at an example of that. So if f of x is equal to this, first I need to do chain rule. So f prime of x is going to be 2 times the inside, the first, okay, times the derivative of the inside. So this is using my log rules. So it's going to first be 1 over my u, which is really that 5 minus x to the 4th, that's my argument, times the ln of 3, all in my denominator, and then times the derivative of my argument, which is negative 4x to the 3rd. And now what I would probably do is write everything so it's in a fraction. So I'm going to say that f prime of x turns out to be negative 8x cubed log base 3, 5 minus x to the 4th, all over that 5 minus x to the 4th ln of 3. And that would be my derivative function. Now, e to the x is actually even easier. The derivative of e to the x is e to the x. The derivative of e to the u is equal to e to the u, so the original, times the derivative of that exponent. All right? So, if I had y equals e to the x plus x squared, my derivative is the original rewritten times the derivative of the exponent, which is going to be 1 plus 2x. And really the only thing I probably would do would be write that 1 plus 2x in front. Okay. Next, if we look at the derivatives of b to the x, so a number to the x, that is going to be equal to b to the x, so the original, times the ln of my base. All right? So if I have b to the u, I basically have to do b to the u times the ln of u times the derivative of u. So that one's going to change slightly. Okay. So in example 4, at what point on the graph of the function y equals 2 to the t minus 3 does the tangent line have a slope? Well, first I need to find the derivative. So the derivative of 2 to the t is 2 to the t times ln of 2. So I need to set that equal, because I want to figure out when the slope of this thing is going to equal to. So I would probably divide through by the ln of 2 equals 2 to the t. And then what I would probably do would be take the ln of both sides. So then I end up getting that the ln of 2 over the ln of 2 equals t times the ln of 2. So then solve that for t. So that would be the ln of 2 minus the ln of 2 all over the ln of 2. At this point, I would probably just use a calculator, plug that in, and that turns out to be 1.5288. And then, careful, the directions say at which point. So I want to find the y value. So I take that and I plug that into the original. And I got that. Okay. Let's try a couple more. Next example, evaluate each of the following. So it's 7 to the negative 3 over x. All right, so I have to use my derivative of a number raised to the x. All right, so that's going to equal the same thing times the ln of 7 times the derivative of that exponent. So if I I have negative 3 to the x to the negative 1. That's really 3x to the negative 2. So that's where 3x to the negative 2 comes from. And then I would probably rewrite this a little bit so that I have 3 ln of 7 times 7 to the negative 3 divided by x over x squared. And then I don't want that negative exponent in the numerator, so I'll probably say 3 times the ln of 7 over x squared times 7 to the 3 over x. And the reason I would just rewrite them is so that I don't have any negatives in my exponent. B is a little bit easier. When I do B, we could do it 2 different ways. You could actually simplify it first and then find your derivative. So remember, if the e to the ln of x is really saying e to the log base e of x, which is really just x. So that's equal to the derivative of just x, which is 1. If you did not see that and you wanted to use your log and exponent rules, your log and exponent rules say you take the original and then you multiply it by the derivative of what's in the exponent, which is 1 over x, and then you would see that you end up getting x over x, which reduces to 1. So either way, the derivative is equal to 1. All right, let's take a look at 1 or 2 more. So for D, I have to do a chain rule. Right, so the derivative is going to equal 2 times e to the negative t plus e to the t to the first times the derivative of the inside. The derivative of e to the negative t is going to be e to the negative t to the negative 1 times negative 1, excuse me, plus just e to the t. And then I might just rewrite it a little bit and say maybe I have e to the t plus e to the negative t times e to the t minus e to the negative t, which I can then simplify and say that's 2 e to the 2t plus e to the negative 2t. That is a difference of perfect squares. All right, I don't want to go through all the algebra in D, but I will give you the final answer. So see if you can work out D to get 2x times 5 to the sine squared of 4x times x ln of 25 times sine of 8x plus 1. See what you can do with that one. Next example, find the equation of your tangent line. All works the exact same way. So they give me a point, so I need the slope. The slope is found by using the derivative formula. Right? So I have that y prime equals. The first, I have to use a product rule. But before I actually do that, hopefully we notice to make our life easier, I could pull out what they have in common. So if you actually factor out an e to the x here, then we only have to do one product rule, as opposed to doing 2 of them. So if you factor out, it's going to actually make your life easier. So I want to do that. So then I'm going to do the first times the derivative of the second plus the second times the derivative of the first. And then if you notice again, these two terms both have an e to the x, so why don't I factor that out? So I have e to the x times 2x plus 2 plus x squared plus 2x plus 2, which gives me e to the x squared. Oh, I messed up my sign. This should be negative. I lost a negative sign, so I just want to redo that problem. I apologize. That should have been negative 2x. Hopefully you guys realize that. I'm sorry. So it's the same principle, but now it's actually going to cancel some things out. Again, I apologize for that. And now by having it in the negative, I now have a bunch that cancels out, so my y prime is actually just e to the x times x squared. So to figure out my slope, so my slope is going to be e to the first times 1 squared, so I just get e. So then to find the equation where my slope is e at the point 1 comma e, y equals mx plus b. My b turns out to be 0. So I get y equals e times x. Right? And then this will be our final example. Find the derivative of just, example 8, find the derivative of this. Okay? So the first one, e to the x times y, is I write down the original, times, and then take the derivative of what's in the exponent. Now that's a product rule. So it's going to be the first times the derivative of the second plus the second times the derivative of the first. And I get dy 2y dy dx equals 0. All right, now I have to get dy dx on one side by itself, so I'm going to distribute and say that I have x e to the x y dy dx plus y e to the xy plus 2x minus 2y so I brought all my dy dx's to the left, so x and then minus 2y. Then I brought the other stuff over, negative 2x minus y. So then I end up getting that dy dx equals negative 2. Alright, so hopefully this was a good preview of some log and exponent derivative problems, and we will continue to work on these throughout next chapter and throughout the rest of the year.